Welcome to the module on goodness of fit. We have spent quite a lot of time figuring out how to get the estimators and how to make inferences in generalized linear model. We have written out the likelihood for the generalized linear model and seen exactly how this differs throughout the case where we have a continuous outcome. The situation in this module is that we have already fitted a model, and having fitted the model, we wish to make some statement about the goodness of fit. Now you all know that when we have continuous outcomes, the way to make a statement about goodness of fit is to look at goodness of fit criterion such as R² or adjusted R². Alternately, we can also define residuals and look at plots to make some inferences about how well our model fits. We shall see in this module that the concept of a residual is not necessarily as straightforward. The reason is that the residual is basically defined as a difference between something which we observe and something which we expect based on the fitted model. Now consider a case where we have a binary outcome. We observe a sequence of zeros and ones. But the model we fit, for example, say a logistic model, is fitted to the probability of y being 1, and hence the fitted logit and the sequence of zeros and ones cannot really be immediately compared. We thus need to extend the concept of expected and observed, and you will see that this is neither straightforward nor unique. We shall define several alternative concepts of residuals. The first will be the Pearsonian residual, which we know already. The second will be two new kinds of residual, an Anscombe residual and a deviance residual. And we shall also see that the three residuals do not necessarily indicate the same kind of information. Now, residual plots, as you know, are subjective, and we may wish to combine these into one single summary statement about goodness of fit. For linear models, this can be done by the R², adjusted R², and a variety of other criterion based on the residual sum of squares. Here there is no residual sum of squares, but there is a likelihood, and we shall define a measure of goodness of fit based on the likelihood called the deviance function. Our first learning objective for this module is to define the saturated model. This is in some sense the best possible model which can be fitted to the data, and the goodness of fit of any fitted model will be judged as compared to the saturated model. Next, we shall define the concept of a deviance function by comparing my fitted model to the saturated model. We shall generalize the concept of a residual from the more familiar linear model setting to the generalized linear model setting. And finally, we shall define some alternative residuals for generalized linear models. So, goodness of fit for the generalized linear model. The first concept we shall define here is the deviance function. Now, recall that when we want to define goodness of fit for the linear model, we do it by basing it on the decomposition of the sums of squares. This, of course, comes from the various vector spaces, the estimation space, the error space, their breakups, their orthogonality. Note that here there is no such space. So, for example, if we try to decompose the sum of squares, we do not get the usual orthogonal breakup, and hence we are not able to easily define the concept of R². This is because our inference is not really based on the residual sum of squares. However, although we can no longer apply least squares and all the associated linear theory with it, what we do have in this situation is a likelihood, and we know that our purpose of likelihood-based inference is to maximize the likelihood. This is exactly the concept which I'm going to use to define the concept of a deviance. My deviance function is thus defined as minus twice log the maximum likelihood for the model, my fitted model that is, and divided by the maximum likelihood for something called a saturated model, equal to minus of 2 L of mu hat y minus L of y. The first term, that is L of mu hat y, refers to the likelihood for my fitted model, written as a function not of the canonical parameter but as a function of the mean of y, mu, or rather a function of the fitted mean of y. The second is similar, but it appears that I have replaced mu hat by y. That is, I have fitted a model which returns y as my estimator for mu. This is the idea of a saturated model. So let us look at it in slightly more detail. Let us assume that we have data on an outcome y, which we assume for now is continuous, and information on an associated single covariate xi. Look at the sequence of models which are given on this slide. The first is the linear regression model, specified by expectation of yi equal to alpha plus beta xi. This is quite a restrictive model. It says that the mean of y is a linear function of x and that there are only two parameters which govern the mean for all n observations, which is alpha and beta. So if we were to plot the fitted regression line for this data, we would expect to get a line and to expect to see all the endpoints lying more or less around this regression line. The second model is the quadratic regression model. So this is slightly more general in the sense that it allows for a third covariate xi squared and a third coefficient gamma. So the quadratic regression model is given by expectation of y equal to alpha plus beta xi plus gamma xi squared. Of course, the linear regression model is a special case of the quadratic regression model in the sense that we would get the linear regression model if gamma turns out to be equal to 0. My third model is the common mean model, which says that expectation of y is equal to mu for all I. So this is the most restrictive of the four models which are given here, and it says that every one of the n observations has the same mean mu, so that if we were to get the regression line from this data, we would expect to see a horizontal line and all the n data points lying around this horizontal line. By contrast, the most general model which I am able to fit to this data is given in the fourth model, which has been referred to as the subject-specific mean model. Now this simply says that expectation of yi is equal to mu I. That is, each of the n observations are allowed to have their own mean and no kind of structure has been imposed on mu as a function of covariates. Note that this comes at a cost, which is that I now have my maximum number of parameters, which is n, one parameter for each observation. Now, you have all heard of the term saturated in the context of solutions. So a solution is saturated when it contains the maximum possible number of solute. Maximum possible solute. In this sense, the last model here is also a saturated model. It gives the best prediction, the best fit, at least to the observed data, because it simply says that yi hat is equal to yi for each I. The cost is at a very high number of parameters. So this model is saturated in terms of parameters, and hence the name saturated model. The deviance note from the first slide is essentially a likelihood ratio statistic. Now, if I'm talking about likelihood ratio statistic, I must be having some hypothesis in mind. The hypothesis here is given by the fitted model holds against a more general alternative. So this more general alternative corresponds to the saturated model. Note that for the one parameter exponential family, the deviance can be simplified as minus 2 L of mu hat y minus L of y is equal to twice summation over I yi theta I curl minus b of theta I curl by a phi minus twice summation over I yi theta I hat minus b of theta I hat divided by a phi. Here theta I hat refers to my fitted model and theta I tilde refers to the corresponding theta estimate from the saturated model. This turns out to be equal to twice summation over I wi into yi theta I tilde minus theta I hat minus b of theta I tilde plus b of theta I hat whole divided by phi for most models, because for many popular GLMs, the function a phi is of the form phi by some constant wi. This I shall define as d of y over mu hat divided by phi, and this is a scaled form of the deviance function. The deviance for the Poisson model, for example, for this model, theta I hat is log of mu I hat, b of theta I hat is e to the power theta I hat equal to mu I hat, theta I tilde is log of yi, and b of theta I tilde is equal to yi. Thus, d of y mu hat is equal to twice summation over I yi log yi over mu I hat minus summation minus yi plus mu I hat. In the case where we are fitting a log linear model with an intercept, by virtue of the score equations, the last two terms will cancel out. So d of y mu hat is equal to twice summation over I yi into log of yi over mu I hat. The deviance for the binomial model is given by twice summation over I ni into yi log of yi over 1 minus yi minus log pi I hat by 1 minus pi I hat plus log of 1 minus yi minus log of 1 minus pi I hat. So pi I hat, of course, refers to my fitted model, and the remaining two terms are from the saturated model. So this is equal to twice summation over ni yi log of ni yi over ni minus ni yi minus twice summation over I ni yi log of ni pi I hat by ni minus ni pi I hat plus twice summation over I ni into log 1 minus yi by 1 minus pi I hat is equal to twice summation over I ni yi log of ni yi by ni pi I hat plus twice summation over I ni minus ni yi into log of ni minus ni yi by ni minus ni pi I hat. Now, binomial data is usually treated as two separate classes of models for GLMs. The first refers to a situation which we call group data, where we have more than one observation corresponding to a particular covariate value, or rather, ni is greater than 1, at least for some of the i's. The other situation refers to something called ungrouped data, where ni is equal to 1, that is, we have exactly one observation corresponding to each covariate value. Now, it turns out that we have some Problems with using the deviance for the case where we have ungrouped binomial data. Substituting n equal to 1 into the expression given here and relating it to the score equations, it is possible to show that the first term in the deviance becomes a function of beta hat. So the deviance is thus a function of the true beta. Assuming that beta hat is reasonably close to beta, it turns out to be a function of the true beta. This is a problem referred to as sparseness in the literature. It suggests that the value of the deviance depends upon the true underlying value of beta. So thus, even if we had a model which, say, did not fit well, it might be possible to get a small value of the deviance if the value of beta was suitably chosen. The fit thus turns out not only to depend on my fitted model but on the true underlying parameter. So this is not desirable, and it leads to a problem with using the deviance for the case of ungrouped data. This problem has been referred to in the literature as the problem of sparseness. Here is the deviance for some common models: the normal, the Poisson, the binomial, the gamma, the inverse Gaussian, and I leave it to you as an exercise to derive these common forms. The common situation where we need to use a deviance statistic for goodness of fit is when we have fitted two nested models. So say we have fitted two models with two sets of covariates where one set of covariates is nested in the other. In such a situation, note that the likelihood ratio statistic can be expressed as the difference of the deviances. Thus, minus 2 L of mu hat naught y minus L of mu 1 hat y is equal to minus 2 L of mu naught hat y minus L of yy minus 2 L of mu 1 hat y minus L of yy. Here mu naught hat and mu 1 hat are the mean estimates from the two nested models, and y of course refers to the saturated model. So this is equal to d of y mu naught hat minus d of y mu 1 hat. Thus the difference in deviance between these two nested models is the usual likelihood ratio statistic for testing the difference of the two models, and we know that for the one parameter exponential family, this difference of likelihoods will have a chi-square distribution, which we can use as a benchmark for testing the difference, the significance of the difference of two deviances. A very useful technique for the case where we had a linear model was analysis of variance. This allowed us to split the total variance of the outcome into several components, some corresponding to estimation and some corresponding to errors, and to further split the sum of squares due to estimation into various subcomponents corresponding to the various constituents of the mean. So for example, for a two-way analysis of variance with two factors, say A and B, and an interaction, say AB, it is possible to fit the total sum of squares due to regression into separate components for the factor A, for the factor B, and for the interaction AB, and to test for the significance of each of these by comparing them to the sum of squares for the error. It would be highly desirable to be able to define something like this for the case where we have a generalized linear model. We do in fact have an equivalent called the analysis of deviance, but because we are missing the usual orthogonality which leads to the break of squares in the linear model, this is rather an artificial concept. So say we have some kind of discrete outcome and two factors, A and B, as covariates. We can define this kind of an analysis of deviance table by mimicking the analysis of variance table. This corresponds to an example which has been discussed in more detail by McCulloch and Nelda. So A is a factor having 9 levels, B is a factor having 6 levels, B is a factor having 7 levels, and this gives me the analysis of deviance mimicking the analysis of variance. The models which are referred to in the first row are respectively the model with no covariates, the model including A. Now note importantly that the third model refers to the model which includes B given that A has been included. And the model on the last line of the table refers to a model including the interaction given that A and B have been included. The interpretation of the corresponding deviances is firstly A ignoring B, B eliminating A, and AB, the interaction, eliminating A plus B. So one important difference between analysis of deviance and analysis of variance is that I could get an entirely different analysis of deviance table if I changed the order in which the models were fitted. So if, for example, I had B first and then fit A eliminating B and so on. As you know, by virtue of orthogonality, such a problem does not arise for the case where we have a linear model. Nevertheless, the analysis of deviance table can be a useful tool, although it might be advisable to consider several alternative permutations of fitting a sequence of covariates. Come to the concept of residual. Now note that the broad idea of a residual is to get observed minus expected. For a linear model, this is very easy because my observed is y and my expected based on the model is y hat, so I simply get y hat minus y. These I know are IID with roughly a normal 0 sigma square distribution, assuming that the original y's are normal. Even if they are not necessarily normal, they are IID with 0 mean and variance sigma square, so we can plot them either against the fitted values and the covariates. The broad idea from a residual plot is that it should be a horizontal band with no pattern. The moment we see a pattern in a residual plot, we know that there is some source of error which we need to go back and investigate. The idea of a residual does not in fact carry over this easily to a GLN. And there are several alternative definitions. So the first is the Pearsonian residual. The numerator is as expected yi minus mu I hat, where mu I hat is the corresponding fitted value of the mean from my fitted model. If I were to stop here, note that GLN data is often heteroscedastic. So for example, for count data, we know that the mean mu I, so say for a log length this is given by e to the power xi prime beta, is equal to the variance, which is also then equal to e to the power xi prime beta. Thus the variance depends on the covariates, and as this is different for each of the individuals, we have a situation of heteroscedasticity. Thus it would not make sense to compare just the yi minus mu I hat difference values, and so we standardize them by the corresponding estimates of the variance, the square root of the corresponding estimates of the variance, to get a residual which we are familiar with as the Pearsonian residual. The motivation for this is, of course, the chi-squared statistic, which is used for goodness of fit of a distribution. An alternative idea for residual comes from Anscombe. It turns out that the Pearsonian residuals, so far we have been spending a lot of time figuring out how to fit generalized linear models, how to extend the family of linear models to the case where we have discrete outcomes. In this module, we have tried to extend the concept of goodness of fit to the case of a generalized linear model. We have defined three residuals. The first is the Pearsonian residual, which we are already familiar with. The second is something called an Anscombe residual based on the concept of transformation to normality. The third is a new concept called the deviance residual, and this is based on a goodness of fit criterion, which we have also defined for this module, called the deviance. We have seen that the forms of the deviance simplifies for the case where we have a generalized linear model. It can be written in terms of the basic building blocks of the exponential family. And we have also seen what the expressions are for some common families.